Hey, what's up? It's Jake from Nimbus DevOps, and I wanted to talk to you about not overdoing comprehensions and generators. So in my previous video, I showed you how comprehensions and generators are much faster than for loops, but that doesn't mean that you should go overdo it and just use them all the time. They're very powerful, and don't get me wrong. Uh, when you have to deal with them, their complexity grows exponentially. And the more you try to do with a single comprehension or generator expression, the harder it actually becomes to read, understand, and therefore maintain or change or update. So if you go look at the Zen of Python, which I referred to before, there are a few lines that are worth keeping in mind when dealing with optimized code. So if you don't remember, if you have Python open, you can just say import this, and it will pull this up for you. Explicit is better than implicit. Simple is better than complex. Readability counts. If the implementation is hard to explain, it's a bad idea. Okay, so now we're getting into this. Comprehensions and generators are more implicit than explicit. It can be quite difficult to read to understand and very difficult to explain. And sometimes you have to break them apart using inside out techniques to understand what's going on. The average person is going to look at a for loop and probably be able to understand that. So to give you an example, look at Pythagorean triplets. So like if you remember like positive integers ABC, like a squared plus b squared equals c squared. And you can calculate them in a filtering comprehension section, which we did, and we did it very inefficiently. And we're scanning all the pairs of numbers to like below a certain threshold and calculating the hypotenuse and filtering out anything that was not a valid Pythagorean triple. A better way to get a list of Pythagorean triplets or triples is to generate them directly. And there are many different formulas you can use, like the Euclidean formula, to say that any triple ABC where A is m squared minus n squared, B is m2n, and et cetera, I'm not getting it into math, but is a Pythagorean triple, and you could do it that way. But there's a catch when you consider a triple like 6, 8, 10, which is 3, 4, 5. Only all the numbers are multiplied by 2. The triple is definitely a Pythagorean, but you can derive it from 3, 5 simply by multiplying everything by 2. The same thing goes by certain other things like 9, 12, 15, and 12, 16, 20 in general. For basically all the triples that you can write as 3k, 4k, 5k, with k being a positive integer greater than 1. A triple can't be obtained by multiplying elements by another by some factor k, and we would call that primitive. So another way of saying that is that if 3 elements of a triple are co-prime, then the triple is primitive. 2 numbers are co-prime when they don't share any prime factor among their divisors. That's when their greatest common divisor is 1. So for example, 3 and 5 are co-prime, while 3 and 6 are not because they're both divisible by 3. So the Euclidean formula would tell you that if m and n are co-prime, then m minus n is odd, and the triple or generate is primitive. So I can write a generator expression to calculate the primitive Pythagorean triples whose hypotenuse c is less than or equal to the integer n, which means that all triples uh, basically are less than n. But when n is 1, the formula looks a little bit different. So if you're completely bored by now, just know that I wanted to give you the more correct answer without assuming that nobody could understand it. If you don't understand any of that or none of that makes sense to you at all, don't worry about it. You don't need to know any of this to be a really good programmer. But if you are trying to get into the weeds with this, that is an example that you can go work out that would help. And I'll get everybody started with what that might look like. So here's a step-by-step version of it in a simple GCD function. So if I define a GCD function that takes input AB, and I'm going to say this is going to calculate the greatest common divisor of AB. Okay, so all I'm going to say is while B not equal to 0, A, B equals B, A, or B, sorry, A mod B. And then I just want to return A. So the explanation of Euclid's algorithms, you can look it up on the internet, so I won't bore you any more than I already have. And the next step is to use the knowledge you gathered before to generate a list of primitive Pythagorean triples. And that gets a little bit more complicated. I'm not going to go over all that right now. But essentially, it's a lot better to go through line by line when you look at doing it with for loops instead of with generators and comprehensions. It's a lot easier to read. Okay, a lot less parentheses, a lot less nesting, but you'll be able to see that a little bit easier. So yeah, so I'll just leave it at that. I encourage you to challenge yourself to try to figure out how would you do a greatest common divisor. Look at Euclid's formula, look at the Pythagorean triples, and see if you can use everything that we've gone over so far to generate those using comprehension, using generators, and using a for loop. And what you'll find is that while you do waste a little bit more time and you take up a lot more space using the for loop, that it is much easier to read and it is much easier to edit. And it's much easier for other people to understand what it is you were trying to do. It's just a lot more readable. So, I guess in summary, don't overdo comprehensions and generators because they can make complex problems way more complicated than they need to be. And always remember the Zen of Python, uh, and just that you can import this and pull it up. And in this specific case, the explicit is better than implicit, simple is better than complex, complex is better than complicated, and that is and readability counts. Those are the things I would take away from when choosing a for loop versus a comprehension or a generator. So I hope that helps. If you have any questions, let me know, and I promise I won't talk about linear algebra anymore. Take care.